All right, welcome to another podcast. This episode, we're going to be taking a look at how to convert equations to systems. This is one of those topics that sort of bridges the gap from earlier in the semester where we were looking at only equations to now being able to take that information and transform it into a system. We actually did this in class a little bit earlier this year where we had a problem we were trying to graph. We had to look at its phase plane, and in order to do that, we had to set it up as a system. So we're kind of coming back to that idea. And I think the best way to start this off is by looking at a numeric example, and then I'll do the problem in general for you after that. So I want to start with bigger than a second order equation just to demonstrate this. So let's suppose that you were trying to solve the third order differential equation given by this. So this is a constant coefficient equation. We could still use the characteristic equation method. We just have maybe a rough time factoring it because it's a cubic. But suppose I wanted to create a system. So this is a third order equation which is going to create a first order 3x3 system. Now the 3x3 just means that you're going to have three variables. It's going to be a three variable system. And the question is, what are the three variables? Because if I can pin that down, then it's going to be really easy to write this as a system. And the best way to do it is by looking at the equation like this. This is the same thing as y triple prime equals, this would be plus 2y double prime. So this would be y triple prime equals minus 2y double prime plus y prime plus 2y. And so I view this as being a function of what variables? Well, there is the independent variable, which we can't even really see in the problem, is t, but it's the independent variable here. And then this right-hand side depends on the variables y, its first derivative, and its second derivative. So because the third derivative depends on those three, if I could write those three as their own separate variables, then I can completely control kind of what's going on in the problem. Those are the variables I want to track independently. See, because as it's written as an equation, all three of those are sort of happening at once. I can't track their independent contributions to the overall system. So to do that, I'm going to set this up to where I'm going to let x1 be y. I'm going to let x2 be y prime. And if x2 is y prime, then that makes it equal to x1 prime. Next up, I'm going to let x3 be equal to y double prime. And I said here this is going to be a 3x3 system because it's a third order equation, so I have three variables, that's all I need. And you can see that here because y double prime then is, so you can see here that x3 is y double prime, which is equal to x2 prime. And then what you look at is, well, then that means that x3 prime is equal to y triple prime. And y triple prime can be written in terms of all of these other terms. For example, you would have minus 2, y double prime would be x2 prime, plus y prime. Y prime is x1 prime, or x2. So probably the better way to write this would be minus 2, it would be x3, and then plus y prime, well, y prime is x2, and then plus 2y, but y is x1. So the point here is I can write each one of these in terms of the others. And so the easiest way to sort of look at this is take these last three equations that I have here, and what they represent is something like the following. You have the dependency now is on x1, x2, and x3's derivatives, and they are equal to, well, you can see that, I'll come back and fill in the coefficient matrix in a second, but they are equal to things involving x1, x2, and x3. So for example, look at x1 prime. x1 prime depends only on x2. So the coefficient matrix would have a 0, 1, 0 because only x2 contributes to x1 prime. x2 prime would be x3, so I'd only have a contribution there. And then finally, x3 prime would be minus 2 x3. and then it would be 1 x2, and then it would be 2 x1. So you can see here that this is the x1 column, this is the x2 column, this is the x3 column. And so I have the system x1 prime equals x2, x2 prime equals x3, and x3 prime equals minus 2x3 plus x2 plus 2x1. And so this is the system view, and then this is the matrix view. So we've managed to turn this third order differential equation into a first order system of three variables. So let's describe what we did here generally. So this is the general rule for doing this. So suppose you have an nth order differential equation consisting of all the derivatives up through the n minus first derivative as dependent equations. Then you let x1 be y, x2 be y prime, and so on, up until xn is the n minus first derivative. So there's your n variable system. So this is the n by n system variables that you're going to need. And the idea here is you just let x1 prime be x2, and away you go. x2 prime is x3, and then this will continue all the way up until you have xn prime, or let's do xn minus 1 prime is xn, and then if you make it one more, xn prime is equal to, well, you can see here, xn prime would be one more derivative on this term, which would be the n term, which is equal to the function f. So what you would have is the function f of t, but all of the variables have now been replaced with x's. So this would be t x1, x2, all the way up through xn. And so this would be the system, and written as a matrix, this actually looks really, really clever. You'd have x1, x2, all the way through xn. So it'd be our n-dimensional vector here. And then the coefficient matrix is what's really cool about this, because if you write our solution vector over here, what does the coefficient matrix look like? Well, because it's not x1 and x1, the ones don't fall on the diagonal. You can see over here when we did the numeric example, the ones fell on the upper diagonal. In other words, the diagonal just above the diagonal. So what this means is we would have zeros on the diagonal all the way until the last row, the second to last row, where we would have a 1 in that value. So we'd have a 0 there, and then a 1 there. And then you have 1s in the diagonal above, and everything else is 0. All that over there is 0, all this is 0. And then in the very last row, what you have is the linear coefficients. So these would be the linear coefficients of the function f. So as I've written it generally like here, f isn't necessarily linear, but if it was linear, then f would look like cn xn plus cn minus 1 xn minus 1. We would have these linear variables. So this would go all the way up to c1 x1. And so what would appear here in the final row would just be those coefficients, c1, c2, cn minus 1, and cn, those linear coefficients of the original equation. So here's the original equation. Those linear coefficients are what are appearing in the last row, and you can see that right here. It was 2, 1, negative 2, so it's the opposite of these. So it's plus 2, plus 1, and then minus 2 are the coefficients that occur in opposite order. So if you read them from right to left, so to get these coefficients here, you're going to read from right to left, because normally we list them in descending order, not ascending order. But this is the basic way that we can convert from a equation to a system, and that's going to be a handy tool for us. The other thing that you really need to get out of this is that the ones in the coefficient matrix appear above the diagonal. So if you ever see a matrix that looks like that, that probably came from a system. That's a very sort of striking result here that's actually useful in a lot of other areas of mathematics, that we have this nice result involving conversion of equations to systems. All right, thank you for watching.